Hello. Why can't you trust an atom like ATOM? Because they're always making stuff up. Yeah. Okay, cool. So let's actually talk about the application of all this plane stuff. Okay. So problems involving the coordinate plane. Okay. Anything to do with the coordinate plane, lines, gradients. Generally, you'll always, where possible, always sketch a diagram. Okay. Even when you'll see later on, we'll talk about letters, you'll always want to sketch a diagram. Now, there's three types of things that we'll look at. We'll talk about collinear, we'll talk about concurrent, and we'll talk about just general kind of like geometrical problems. But if they ever say collinear, if they want you to prove that 3 points are collinear, it means they're trying to prove that they lie on the same line. Okay, now what I've written here is generally there's 3 points, A, B, and C. And if you can find the gradient between A and B, for example, and A equals C, and you show that they're exactly the same, they should be collinear. Okay, or it could be the gradient of AB is the gradient of BC. As long as you've proved that two different sets are the exact same gradient, you've proven that they are actually on the same line. I'll give you an example. Let's prove that 2, 3, 1, 0, and 6, 7 are collinear. I'm going to start off by even just giving myself a rough idea of where everything is. Okay, so I've got 2, 3, 2, 3. I'm not even going to 2, 3. Let's say that's 2, 3. I'm going to have negative 1, 0. So let's say that's minus 1, 0. And I'm going to have 6, 7. Sure, something like that. And I'm trying to prove if these three lie on the same line. So if that is, let's say, A, B, C, if I can prove that the gradient of AB is exactly the same as the gradient of BC, that means that's the same as that, and it's one straight line, then it's collinear. And let's try it. The gradient of, remember your gradient formula is y2 minus y1 over x2 minus x1, and I'm just going to do this as is. So the gradient of AB, let's talk about 2, 3 was B, that's A, that's C. So if I'm talking about AB, it's going to be y2 minus, all right, y2 minus y1. So I've gone 3, take away 0 over x2 minus x1. In this case here, that equals 2. 3 on 3, that equals to 1. Okay, let's double check what's the gradient of BC now. If it's BC, let's do y2 minus y1, so it's going to be 7, take away 0 over x2 minus x1. And so that's going to be 7 on 7, that also equals to 1. We've proved it, therefore collinear points. Okay, they're on the same line. Good. Concurrent, 2, 3 lines. Okay, we're talking about 3. Before, when we're talking about collinear, we're talking about points. Okay, but if we're talking about concurrency, we're actually talking about 3 different lines. We say that 3 lines are concurrent is if all 3 lines go through the same point. Okay, when I say L1, L2, L3, those are the 3 different lines. The way that we'll do something like this is you'll want to solve one pair simultaneously to find their intersection point. And then to prove that the other line goes through it, the way that you do that is just by substitution. So question would be prove if 5x, take away y, take away 10, or basically prove if these 3 lines are concurrent. Okay, so if you want a visual idea, it means that let's say there's 3 lines, maybe 1, 2, 3. Let's say there's 3 lines go through a single point. That's what concurrent means. So like I said, let's prove that 2 of them, let's start with these 2 first. All right, L1, L2, L3. So let's do L1 and L2 simultaneously. Okay, so let's say I'm just going to write this. I'm going to say y equals to, this is from line number 2. Y is going to equal to minus x plus 8. And I've just done that by rearranging. push it to the other side, and then let's sub it into L1. So this is going into your whole simultaneous process. I'm hoping that this won't take long at all. 5x take away minus x plus 8, because that's y. Take away 10 equals to 0. And let's just expand it out. 5x plus x minus 8 minus 10 equals to 0. That's 6x equals to, I'm going to move it over to the other side, 18. X equals to 3. And if x equals to 3, then y is going to equal to minus 3 plus 8. And that's going to give me 5. Okay. So that means our solution is 3, 5. Now, the last step here is I've found the point. I want to sub. The way that it works is it's a prove, but we do that by substitution. Prove 3, 5. Sits. Why did I say fits? Sits on line 3. Okay, so that means 2x minus 3y plus 9 equals to 0. Let's replace x with 3. Let's replace y with 5. Let's see how we go. 6 take away 15 plus 9 equals to 0. Is that correct? Yep, it's true. And therefore, lines are concurrent. Okay, because I've proven that there's an intersection point, and I've proven that the third line also goes through that intersection point. Okay, hopefully that makes sense. Last one, geometrical problem. Now, just remember your general geometric rules here. You'll need to remember things about scalene, right-angled, equilateral triangles. Basically, scalene is no equal sides. Right angle means that there's a right angle. Equilateral means it's 3 equal sides. The other one that I didn't put there, which we're going to use, is don't forget isosceles. And then the other geometrical things that they love to play on is just remember the difference between a square, a rectangle, and a parallelogram. And I can't stress this enough. Draw a diagram, okay, and work one step at a time. So it says here a triangle is given by a naught, 0 or naught, a root 3, and I should have written pretty sure it's 3a 0. My bad. Okay, so let's just think about this logically, and we're trying to prove that ABC is isosceles. So first thing I'm going to do is I'm going to draw something to help me make sense of it. Now A0, let's just say that's something, I don't know, there. Okay, that's A0, that's that point. That means 3A0, I'm assuming, is somewhere a little bit further on, because it's triple of whatever A is. And then I've also got this 0 and a root 3. So that means that's 0, a root 3, whatever that is. And so essentially, I'm trying to prove that this triangle here is somehow an isosceles. Okay, let me just label that's A, that's B, okay, and that's C. So how do I prove that something is isosceles? Hopefully you recognize that that means I need to prove that 2 lengths are equal. Okay, and 2 lengths are equal, and I should say it's only 2, because if all 3 lengths are equal, then we've got a equilateral. So let's talk about the distance, because we're talking about lengths. Let's find the distance of A and B. Let's find the distance of B and C. Let's find the distance of A and C. All right, distance of AB is going to be 0 take away a root 3 squared plus a take away 0 squared. And let's see what that gives us. That's going to give us 3a squared plus a squared, which equals to 4a squared, which just gives us 2a. Okay. Let's try the next one. By the way, if this arithmetic is a bit too quick, I apologize. Maybe slow it down and see where I'm getting these from. I'm using my distance formula here. Now for B and C, I'm going to go, let's see, 0, take away a root 3 squared plus 3a take away 0 squared. And this gives me 3a squared plus 9a squared. And that equals to 12a squared, square root of 12a squared. Not a real nice one for that, so I'm going to keep it as is. Let's try prove this last one, A and C. Let's see how we go. It's going to be y2 minus y1. So 0 take away 0 squared plus x2 take away x1 squared. This is going to give me the square root of 0 squared plus 2a squared. That's going to be the square root of 4a squared, which is going to be 2a. So you can see, after we've gone through all that, two of your sides are the same. One of your sides is slightly different. Therefore, isosceles. Okay. Hopefully that makes a bit of sense. Good luck, all the best, and I'll catch you guys in the next video. Bye.